AI field, AI area. So so thanks Tian and Hong to organize this workshop and invite me, and thanks MBZU AI support this event. And today I'm going to share some my understanding of my naive understanding of deep neural network for imaging data analysis. So as I'm training as a statistician, I didn't learn quite well about the AI or machine learning algorithm during my PhD studies, but later this area, everybody talks this area. This is a very exciting area, and it works very well in many applications. And now I began to try to understand and kind of take some effort to study this method in my field, the neuroimaging studies. So basically, I think Hong Tu gave a very nice overview of the entire medical imaging field. What I'm talking about here is a little bit narrow and only focused on brain imaging application. And here is some common goals in brain imaging study, like activation study, which is related to imaging segmentation problem, but is particular for brain activation. So, and also co-activation or connectivity studies, and also in neuroimaging there's prediction classification problems, and I have been doing some meta-analysis, and recently we are doing some multimodal imaging, integrate different type of brain imaging. And so I think I have learned since my PhD study, so it's important to start from application to analyze data, and also important to start from simple model, simple things. You try very simple model to a data set, see what's going on, and then whether there's needs to make it complicated, right? So this is something like regression analysis or linear regression as the most powerful kind of statistical models I have learned so far, and I'll try a lot of a data set, a linear model actually works reasonably well, and of course not necessarily the best model, but it always works. And in imaging application, I primarily work on several type of regression, like image on scalar regression, or scalar on image regression, or image on image regression. So basically it depends on you put the image as a response variable or as a predictor variable, or both. So, and they actually have a different goal to try to understand different kind of like brain activity or different aspect of the brain imaging research. So, but here I try to maybe give some answer to Jakob's questions about deep neural network or deep learning is a statistical method, or which model we should to use. So actually we try both like linear model, and if you using deep neural network in this type of regression, what's going on. So this is some our recent effort. So well, the first one is this like a image response regression. So if you put image as response, and you put all the scalar covariates, scalar variables as covariates, so can we this is actually quite a simple model that you can apply linear regression by each location of the brain, and then you can get this so-called massive univariate analysis, and you can actually get estimation of the parameter. And the idea here is that because the signal to noise ratio is relatively low, and there's a heterogeneity among the subjects and the data set. I mean, traditional neuroimaging studies, the number of subjects relatively small, but nowadays they have increased a lot. But compared with the resolution of the image, like thousands, hundreds of thousands of voxels in the brain, that's sample size still relatively small. It's not like computer vision kind of sample size. So in this case, we're trying to bring in the deep neural network to model the spatial invariant coefficient in this type of the model, and we gain some like a very interesting results that basically, if you compare with the traditional statistical method, like a non-parametric method, like a kernel method, like a spline, and other like non-parametric regression type of method, like low rank approximation with sparsity. So those all methods just handle this type of this is a kind of simulation study. Like so you can see that from the very basic method, like the massive univariate method, and this simple linear regression. And if you do kernel method, this is panel B. And if you do the low rank approximation, where if you do some smoothing after linear regression where you do spline, and they compare with deep neural network. Actually, deep neural network can do almost a perfect recover the true signal. And this is actually not a quite easy design because we try to have a sparsity on the true signal first, and also we have a very high level subject level heterogeneity. So when you observe data, the data is quite noisy, and also the spatially adaptive, like some smoothing, are quite different across different locations. If you want one simple traditional statistical method actually cannot achieve to recover this very well. So, and this is the sort of powerful of the deep neural network. Here, one special like using deep neural network, you can design the output layer using thresholding, like a kind of activation function, then you don't even need to use any shrinkage method like a penalization method. You can achieve sparsity, exactly sparsity, and then you can avoid to use like all type of regularization method in the model feeding. And we actually have the theory show that it works well, at least for this image response regression. And another kind of effort we have made to try to simplify the deep neural network for the particular images, scalar image regression model. So the idea here is that because we know some like brain structure and location information, whether we can just simply build in that information into deep neural network, and even we don't need to go very deep. We actually start from just single layer neural network. So everybody familiar with neural network theory, that is that one layer single layer neural network actually has uniform approximation theory that you actually can recover any continuous functions in arbitrary accuracy. But basically the number of the nodes in the layer is important here. But here we're trying to bring the brain structure information, and we can actually achieve much better performance and compare with like a state-of-art like a convolutional neural network method. So basically, there's some opportunity if we incorporate neural imaging like prior knowledge, like a brain prior knowledge, you can actually simplify the neural network and actually achieve quite comparable results compared with state-of-art like a convolutional neural network. And another effort we are recently trying to kind of integrate the deep neural network with some other machine learning method like Gaussian process or SVM. So this is something like we build up the some important parameters like kernel parameters in the the Gaussian process, and we actually using deep neural network to construct the kernel instead of like directly apply deep neural network. So that actually can achieve better interpretability, and this is a very complicated task that you use one set of the neural imaging. In this application, we motivated by using resting state fMRI to predict task fMRI, and we actually can handle a very large dimension of the input and both the predictor image and our response image, and also they not necessarily in the same imaging space, and they can be very flexible. And if you kind of combine the deep neural network with the Gaussian process, you actually can achieve much better performance. Here is one example that we can identify which part of brain is sort of predictable, and if you compare with like a regular voxel by voxel image on image regression, or like a just simple linear regression, and the original paper from Science to address this topic is based on this linear regression problem. Then they cannot find any region of the brain actually predictable. But based on this new method, we actually can identify quite a few regions of the brain are predictable from the resting state fMRI to the task fMRI. So this is three examples I want to share here that basically my view of the deep neural networks is my naive view. It's definitely part of the statistical model. So and it's actually can be integrated with classical regression model or other statistical models we have been quite familiar with, and it depends on how you actually use it, and it can be simplified or modified for your purpose. It depends on your application. If you quite understand your application very well, you actually can design a kind of like user-specific neural network for you to improve the performance. And if you combine the deep neural network with other machine learning tools, you actually can boost the power. Depends on how you do it. And there are some research topics I'm quite interested in right now. One is how you using deep learning to help you do the experimental design. I have been working on one application like brain-computer interface that you actually can design using machine learning algorithm help you to design to collect data by yourself. I think it's important that we know how to do the image acquisition, and then we can collect the data by ourselves. Then we can better actually do the analysis. So I think a lot of like data set is not if it's not collected as what we expected, we need to do a lot of effort later to actually find a signal. But if you collect it correctly, then it's very easier to you to find a signal. So I think other important topic like in my view is like manifold learning, with instead of like do the voxel-wise selection in the neural imaging, you summarize the signal. Globally from the brain. That's important. That's a part of manifold learning, and also we are doing some data integration and causal inference. And another important topic we recently start to work on is prediction and uncertainty quantification. So I'm trying to understand whether this problem is predictable using the given set of the predictable. So how you define predictability. So how you actually can define formal statistical measure to measure on that. And also we want to, so you think about the prediction actually can be very hard, it can be very easy. For example, I can predict in the next second, everyone's gonna sit here, no one stand up. Yeah, this prediction 100% correct, but I cannot predict in the next hour, everyone still sit here. Right, so this is going to be quite different things. So it depends on how you measure that and how you actually formulate the problem. So, and I think in this area, there are kind of promising AI techniques like a large language model and generative model, especially for the imaging related, computer vision related generative model, and reinforcement learning like deep Q network is very popular and useful for the experimental design problem, and also transfer learning has been very useful for the data integration. So there are some very important issues. I think Hongdu already addressed most of them. I think I think we need a scalable and affordable computation from both hardware from perspective, also like the students need to know how to programming very efficiently. I think from statistical or biostatistics department, their programming has improved a lot, but I think not comparable with computer science people. So it's still like that's a major barrier of our implementation of the ideas and research. And also I think I hope we can have like ImageNet based like medical imaging for a large database, but it's very hard, as Hongdu mentioned, a few challenges here. And also, I'm very interested to see all your opinions about theory development. I think Hongdu mentioned that a little bit. So should we shift our theory development like a way, or not necessarily a way, or at least in addition to the traditional statistical model asymptoticals? So what type of theory we should look at for this new model involved deep neural networks? And I think this whole process is a learning process for myself, and I think we have to keep learning and also think about what's the best strategy training next generation of statisticians. That's all my thought here. Thank you.
Great talk. I think for me, for most of the regression problems, I would be just use pre-trained models like from the CV, like foundation models, and basically as a building block for the traditional statistics. I think they should be performed much faster than you train a model from scratch.
Do you mean the CNN or?
No, this is INO, these kinds, they have a lot of different, the pre-trained models based on the existing data sets. Because that's just like, you dump your imaging data, your medical imaging data, and you get all the features. And then using traditional models to do everything afterwards.
Okay.
Because without basically your trained model from scratch. But your kind of most of the
so
models.
So it's more like the transfer learning part of type of.
Not transfer learning. It's more like you dump the imaging data into the neural network, the existing trend models, because you know all the weights and the hierarchical the architectures. You just the kind of transfer the data to another dimensions
I see.
and do all the
I see.
traditional statistics.
Yeah.
That's one of the key reasons they try to build these foundation models and for different applications. Then that's the make this feasible in practice. In like app, they can easily do it in practice without basically build everything from scratch.
Yeah. Thank you.
Great talk. So quick question. So what is the major bottleneck for building the large database for medical imaging? What do you guys think?
Yeah, I think there's a very complicated like pre-processing steps that, and yeah, there's I think for different type of the imaging and also for different experimenting sites collecting the imaging, they have different machine and different acquisition procedures, and and also there's some like issue about the sharing data.
Sorry. So in my applications and collaborative projects, I work a lot of other type of imaging data. For example, dental imaging, where we study our health from kids and trying to find some our diseases, by looking at imaging data. And also we look at some like wound size from like diabetes patients. That when patients have the severe diabetes, they start have a lot of the wounds and ulcers on the foot, so that they may need to go through the surgeries like amputation or something like that. So I don't know, like when you work on all the imaging data, whether or not those deep learning or whatever segregation algorithm could be applied to other imaging data. I know that the brain imaging is very challenging, it's very sophisticated, but I wonder, like for my sort of application, I say whether or not your method can be applied, or you have whatever method developed can be applied to other type of imaging, so we don't need to develop our own method to deal with our imaging data. Do you have this generability or applicability of your method to other fields? I hope that when you write a paper, you can use different type of imaging to show the generability, so that we can use your method to our field.
Yeah, I think that's a very good point. So the current method we develop, I think for the image regression, we can do that. So for any type of the imaging, not necessarily the neural imaging. So any medical imaging, as long as we can use deep neural network to regenerate that image. So if you can regenerate that image, and then we can actually build up the method to do prediction and also to do the model fitting. And for the first project, that is a very, very simple idea to apply neural network that require you have to register image in the same template, same space. In that case, maybe other type of image not necessarily applicable here. But I think the power of the neural image, the power of the deep neural network type of the method include those generative models. They can actually fit any type of image, even they are not registered very well. And in that sense, you can actually project the image into dimensional space, lower dimensional space like latent vector space, and then you can to align them in a lower dimensional space, and then you can do the regression model. Yeah, that's potentially definitely, but that quite depends on the specific applications.
So I'm curious, because you also mentioned that now there are many generative models, right? Can help to generate. Then is your model good enough to generate a lot of medical images that represent? Then we do the segmentation on the generated. Why do you still need actual? If your task is like segmentation, why would you still need real images?
So the generative model is more like can be used to represent the observed image. So you can generate the image quite similar to observed image, and then in that model, if you can kind of extract useful feature from the generative model, you can actually get those parameters, and using those parameters to do the subsequent analysis. Basically, that's the idea. So just like a large language model, you can generate a lot of words and sentences actually to represent some ideas, but there are some key parameters and the structure in the model can be used to those parameters can be used to build up the latent structure regression later.
Yeah.
Yeah.
Yeah. So regarding uncertainty quantification, so can you give specific examples in your applications? Is it just the dimensionality of your image that makes the problem challenging, or is there like something more specific to this application?
Yeah, it's a very specific, like, so in this example that we're trying to kind of look at the, at which location of the brain actually your social, like language task of the brain activity can be predicted by the just resting state of brain activity. So in that case, we want to identify which part of brain actually quite related to that. So in this case, you can see this is not an exact uncertainty quantification. It's based on our kind of empirical results to see the predictive R-square. So you can see in some of the brain, like front lobe, you can be quite a while predicted. So in that case, our goal here is not show this. Is like given the data, whether we can actually predict, give the measure of each location, whether this location can be predicted or not predicted.
So it's like a prediction interval for a pixel, or like something?
Right. Yeah, you can construct prediction interval. That would be one measure you can consider. Yeah.
Thank you.
Yeah. All right. Thank you.